All right, class. Well, after our review of electrostatics in general on Friday, we're now in a position to construct a simple model to think about how ions are solvated microscopically in a polar solvent. So today's lecture will be on just that, on the electrostatics of solvation. So to do this, we need to take in those lessons of electrostatics and build a simple model of a polar solvent. So that's where we're going to start, by teasing out a simple model and then understanding how it implies such a solvent would react to the insertion of an ion. Okay. So the first goal is to build a simplified model of a polar solvent. So what we're going to imagine is that we can pick out in our polar solvent, something like water, some region of space, which we can then carve up into cells, our favorite thing to do. And in each one of those cells, rather than trying to convey all of the complex microscopic information within those cells, what specific water molecules are doing, we're going to focus rather on a kind of coarse-grained or a simplified picture of what those molecules are doing in regard to what that implies about their electrostatic environment. Water, as a neutral species, then to first order contributes a dipole. So we can, within each one of those cells, imagine that there is a fluctuating dipole. So we'll draw those dipoles with those little arrows because, of course, they are vectorial quantities having both magnitude and direction. Now, we should keep in mind that what we really mean microscopically within one of those cells is indeed that some collection of water molecules is aligned such that it would have generated that dipole. So if I was to draw some collection of water molecules like so, they are pointing in such a way which would be consistent with the generation of a dipole, say, in that direction. Let's draw that little dipole in here. Something like that. Okay. So now within each one of those regions, which are microscopic, we're imagining the cells are something on the order of, a few angstroms, maybe a nanometer, large enough that a few molecules, more than one, but less than 100, can occupy it. And within each one of those cells, we're going to define that local dipole as M of R. So it is the net dipole in a microscopic region whose location is given by that R vector. This is a quantity that will fluctuate as the water molecules reorient themselves. And it fluctuates around an average, and we know what that average should be. If that fluid has no walls that are meaningful or no species in it, no ions that break the symmetry, then water molecules should be equally likely to point in all directions, which implies that the average dipole in any one of these cells, absent a charge, should just be 0. So M of R is the local dipole in the region R, which fluctuates due to thermal fluctuations about some average of 0. So that's our simple model for a solvent. And we can ask within that model, what happens when a charged solute is introduced? So we know, if we were thinking microscopically, if we took our liquid and we placed an ion, say an anion, in that liquid, that water molecules would arrange themselves in very particular ways. If this really was an anion, we would know that the hydrogens of water would like to be close to it because they contain a little bit of a positive charge. So for example, a configuration might look something like this. So what was a uniform distribution of orientations changes when that ion is present. The water molecules reorient themselves. From the perspective of electrostatics, what that means is that the surroundings, the solvent, become polarized. Polarization is just another way of saying that the surrounding dipole, that in the surrounding of the ion, there is a now non-zero dipole present. So we can denote that dipole in the presence of the ion with our brackets with a subscript ion. That average is no longer going to be 0. And because of the field generated by that ion, and subsequently polarization of the dipoles, the potential energy of the system is going to change. And in general, the energy is lowered. It is favorable for that polarizable solvent to interact with the ion, often by a significant amount. Now, we discussed last time that Coulomb interactions, those fundamental interactions that are governing this electrostatic response, have a particular quality associated with them, which is that Coulomb interactions are significantly longer range than most other molecular interactions. Because they are long range, that polarization of the solvent in response to the ion is not going to be local. In fact, it's going to be very long range itself. Many molecules are going to contribute. And because many molecules contribute, just as in our discussion of critical phenomena, that's going to afford some simplicity. That's going to allow us to say something pretty simple. If we had to worry about the particulars of how those hydrogens reorient in response to some anion, well, that would require a detailed understanding of how that anion interacts with the particulars of the water molecules that would be pretty complicated. But because the dominant contribution of those interactions is electrostatic, and electrostatic interactions act over long distances, a lot of those details will wash out, and we can consider only, this very simplified model of water acting as a set of dipoles. So to actually make quantitative statements about this solvation, we need to actually codify this model of dipoles on a lattice with some mathematics, to actually write down mathematically what the energy of such a system might be and how it will change when an ion is introduced. So let's write that model down now a little more specifically. So first, if we think about dipoles on a lattice, well, if I have two dipoles, we know that they interact with each other. And so I'll need part of my energy function that says how likely I am to see specific configurations of that lattice. Part of that will need to account for the fact that those dipoles in different lattice cells interact, but we know how dipoles interact. That was something we wrote down last lecture. If I have a dipole M and another dipole M prime, the interaction energy between those two dipoles scales like the distance between them. Say if M is located at R and M prime at R prime, that interaction energy is proportional to that displacement to the third. And then there is a factor that tells you about how those dipoles are oriented relative to each other and relative to their separation vector. So there's a piece, as we wrote down last time, that asks for how the dipole at R and the dipole M prime at R prime are oriented relative to each other. You ask for their orientations by taking a dot product between those two vector quantities. And then how they are oriented relative to the displacement vector, which I can compute by taking a dot product of M with that separation vector. Now this is the unit vector. So that's a parentheses. And I do that for both M and M prime. There you go. So that's the interaction energy between two dipoles. Let's try to give that a little bit more space. Clear that up. All right. Just as we had before, two dipoles interact. So that is the only interaction term we'll consider. We'll just imagine again that this solvent is just made up of dipoles on this lattice. And so the interlattice interaction is just dipole-dipole interaction. But in addition to that, we must describe something within the cell. And for example, we need to say how likely it was to have generated that dipole in one individual cell. And we can imagine that in general, it's going to cost free energy to align those water molecules, to orient them in such a way such that I create a dipole. Because those molecules are free to orient themselves in any direction, the likelihood that they're pointing all in one specific direction in the absence of any field that makes it energetically favorable for them to do that, it must be some positive free energy, because we know that the average is 0. If we focus on just one cell, let's have U naught of M vector be the cost to develop that local dipole. This is going to codify the probability that those water molecules, in the absence of any external field, spontaneously align in some specific direction. Now, what might that function be? Well, it's probably a little complicated. Again, the microscopic degrees of freedom, how those molecules interact with each other would probably be important. We're going to take, for this function, the simplest possible model we could imagine. Namely, if we were to draw it pictorially first, so U of M as a function of M, say the dipole in just the x direction. Well, we know it has an average of 0, so that means that that function has a minimum at 0. It has to be symmetric. Likelihood of pointing in one direction in the absence of a field should be the same as pointing in the opposite direction. So then the lowest possible model would be something that just looks parabolic. So we'll have that U naught, the free energetic cost to form a local dipole, should be proportional to the magnitude of that dipole squared. Let's define the constant of proportionality as 2 alpha. Which immediately tells us that if we wanted, again, just focusing on one cell, the probability of seeing some dipole, say in the x direction, given that energy, Boltzmann would tell us that that probability is just proportional to e to the minus beta, the x component of that dipole, quantity squared, divided by 2 alpha. So this should remind you of the Maxwell-Boltzmann distribution. I have some vectorial quantity like the velocity. Because the energy is a sum of the x, y, and z components, the probability of one of those components is independent of the other two. So if I ask for the probability of just mx, that is just a Gaussian distribution with some mean 0 and some variance, which we can just read off, given all of our experience with Gaussian distributions. The variance of the x component of the dipole, well, first, there is no average. The average is 0, so that means that the variance is just equal to the average of mx squared. And that variance, sitting in the role of the variance in this energy function, is alpha divided by beta. So the scale of fluctuations is set by this alpha quantity. And that's true for one component, just the x component. But because all of them are the same, I immediately also know what the variance of the whole vectorial quantity is. It's just going to be all three directions act the same. So that's just 3 times the variance of one direction, which we just reminded ourselves was the same as just the squared average of one of those components. I have 3 components, so I have a factor of 3 to relate the magnitude to the individual component. Putting that all together, I have 3 times alpha over beta. That's the variance of the total dipole. So then again, just to say in words, alpha then sets the scale of dipolar fluctuations. Now, we can already gain a lot of insight as to what's going to happen to this solvent when an ion is present by thinking through just what happens with this one individual cell. So we can ask what happens, for example, when this cell feels an electric field from the surroundings. Let's call that electric field C, as we had before. Well, the energy of that cell is the energy that it had before, U naught. And the way fields interact with dipoles is something we derived or discussed last lecture. The field dipole interaction is just a dot product between those two objects. So the potential energy of a dipole in an external field is given by the field dotted into that dipole. Graphically, the implication of adding an external field to this individual cell is to take the original parabolic function, U naught, subtract from it a line with slope minus the field. If I sum those two contributions to the energy, what I will get when I subtract a line from a parabola, I keep a parabola, but the minimum of that parabola shifts. And so now, instead of, say, looking at just the x component of these quantities, instead of having a minima at 0, I now have a minima at some finite value. So now, say the x component of that dipole on average would no longer be 0, but would lie at the minimum of this new function u. If it lies at the minimum, we can compute what that average is by taking a derivative. So if we took a derivative with respect to mx of u naught minus that field dipole interaction, setting that equal to 0 will give us the value of that minimum. First derivative, well, that u naught was a quadratic function with scale alpha, so we get an mx over alpha. Dot product of the field and the dipole picks out just the x component of the field. Setting that equals to 0, we can solve for the average value of mx as being given by something proportional to the strength of that field with a constant of proportionality, which is alpha. If we were thinking about all three components, the average dipole in response to the field is given by alpha times the full vector field. So now we kind of understand what that alpha really means. Alpha is setting the response of that dipole to a field. So that's a quantity that you have undoubtedly heard of before. If I took a system of charges and I added a field and asked for how much they polarized in a response, well, if you think back to something like 128, that's not so different from saying I have, say, a hydrogen atom, net neutral molecule. It has no dipole on average. If I added a field, I could polarize the electrons around the hydrogen nucleus. The degree to which I generate a dipole due to that field, you call a polarizability. And so that alpha is indeed nothing but the polarizability of one of those cells in our model of a solvent. Now, notice what we've also just arrived at. The average dipole due to adding a field was given by alpha, but also the mean squared fluctuations of the dipole in the absence of a field was proportional to alpha and a factor of kBt. So what we've just stumbled upon is that alpha is both the response of a field, of the dipole to a field, and determines the scale of fluctuations. Let's do this for the vector quantities. So again, as we've found in many other cases, fluctuations in the absence of any field determine the response in the presence of a field, or generally fluctuations and response are intimately related. Okay, so we've just worked through, so we've written down first how dipoles interact between cells, and now we have a model for how the dipole is generated within a cell. So we're in a position to write down the model for the full solvent. So let's denote that energy E. I need to sum over all the cells the energy required to create a dipole within one of those cells. That's that quadratic function we just postulated. In addition, I have interactions between dipoles. So I need to sum over all pairs of cells that interaction energy, which depends on the dipole in cell at R and the cell at R prime. And now, in addition to that neat solvent, if I added a solute, that solute, if it were charged, would generate a field. Instead of calling it ion, let's call it Sol. The field dipole interaction is the dot product, which we just reminded ourselves of. And so in the presence of a solute, the additional component to the energy would be the sum over those field dipole interactions. So again, the three components are the field due to the solute and how it acts on the solvent, the dipole-dipole interactions, that term is going to be what makes this complicated. This is an interacting model. So when we include explicitly interactions between the two cells because of those dipole-dipole interactions, that means that the dipole in one cell is not going to be independent of the dipole in another cell. It's going to make solving for things like the partition function really difficult. Okay, but let's see what we can do with this model. And let's think about specifically ion solvation now. So let's work through what's going to happen if I put an ion in this solvent. So the first thing that's going to happen, if I put an ion in the surroundings, that ion generates a field that will act on those surroundings. Now this is a specific field due to an ion, so let's call that subscript ion. And what might that look like if this is an anion? Again, the electric field we can draw around that ion. Electric field is the force of a test charge due to that ion. The test charge has a positive sign, so the field lines act towards the ion. A positive charge would be drawn towards that negative charge. So that's what the field would look like. Again, the field is a vector. It has magnitude and direction. The direction is isotropic about that ion. Now what's going to happen? So the ion is placed in the solvent. It generates an electric field. That electric field then is going to polarize the solvents in response. So the solvent dipoles respond. And by their response, what we mean is that they will polarize. So if I was going to draw our little slab model, our little cellular model for the solvent, we have a ion in the center. Those dipoles like to align with electric fields. So those dipoles, if we were to draw them as we did before, because we know what the field looks like, we know what those dipoles would look like. Those dipoles would align, and the amount that they will align, the dipole generated in any one of those cells due to the field from the ion is going to be proportional to the field. That's what we worked out a second ago. That constant of proportionality for an individual cell, we know exactly. If those cells don't interact, that would have been just alpha, the polarizability. But now things are a little bit more complicated. We should expect that if we generate a larger field, the dipoles will align more in response. But because we can't neglect the fact that the dipoles interact with each other, when I align a dipole in response to the field from the ion, I am creating unfavorable interactions between one of those dipoles and its neighbor. We alluded to this last lecture that dipoles next to each other tend to want to align anti-parallel with respect to one another. So that means that by polarizing in response to this ion, I'm facing a competition between gaining a favorable energy due to aligning with the external field, but generating a field that my neighbors, the other dipoles in surrounding cells, aren't necessarily happy with. In fact, they would want to then turn around and align in the opposite direction. That means that the constant of proportionality between the generated dipole in any one of these cells is not just what it would be in one cell, but is some complicated function of what a single cell would do and how that satisfies the interactions between all of the other cells. So that's just words that the specific proportionality constant is going to be complicated because of those interactions. But we know that it should be proportional to the size of that initial field. Okay, so we've generated a field by putting an ion in the solution. The solvent has responded. Now what happens? Well, the field generated by the solvent then acts back on the ion. Let's call that field the reaction field. It is the field generated by the reaction of the solvent due to the initial ion field. And we know how fields look like emanating away from dipoles. So they go like the size of the dipole at some region R. And they die off like 1 over R cubed. Now the reaction field at some particular point in space, let's not give that a subscript, at any point in space is going to be some complicated function, say let's say the value. Let's say this is the ion at origin. So this is the field back on the ion at the origin. It's going to be due to the field generated from all ions in all other cells. So I have to sum over all of them. So again, pictorially, this whole procedure, what it's done is an ion generated a field that served to polarize the solvent. The size of that polarization was proportional to the field the ion produced. And now that field generated by the dipoles, by the solvent response, will act back on the ion, producing a net favorable interaction. And because that reaction field is proportional to the size of the dipole, and the dipole is proportional to the size of the ion field, that reaction field is similarly going to be proportional to the original ion field that's kicked this whole process off. So again, just the same words, this should result in an energy which is very favorable. So let's define that energy, or the change, due to an ion spontaneously being present in the solvent. We'll call it delta E solve for solvation. That's the interaction energy. Between the ion and the surroundings on average. So the energy of the ion can be thought of as that energy between a charge and a dipole, or a set of dipoles. The energy between a charge and a set of dipoles can be written as the field of the ion dotted into the dipole. Now that dipole is the dipole generated by the ions. And then the total energy of solvation will be due to summing up all of those dipole ion interactions. Now, of course, as we just discussed, the size of the dipole generated in response to the ion is proportional to the field generated by the ion. This whole process will go like, or scale like, the field of an ion generates squared. So this should be proportional to summing over all spatial cells is like integrating. So I integrate over all space. The field due to an ion at the origin goes like its charge. Let's call it Q ion. And that's our inverse square law due to Coulomb. So that's the field of the ion. The net dipole, we don't know what it is exactly. That constant of proportionality is complicated due to interactions, but it's going to be proportional to that initial field due to the ion. So go like another one of those terms. This means that this whole process scales like the negative charge squared of the ion. The field of the ion is radially symmetric, so we need only integrate over r. We can integrate over the other two spherical coordinates, get a factor of 4 pi. The remaining Jacobian for spherical coordinates gives us a factor of r squared. And we multiply two of those 1 over r squared together. We'll get a 1 over r to the 4. And now the upper bound of that integral can be taken to infinity. R squared over r to the 4 is going to be something that converges. But the lower bound has to be something we specify and remind ourselves of the kind of microscopics of the system in doing so. Namely, we are thinking about the interactions of the ion with the field generated by the solvent. So that field should not be able to penetrate into the ion. So the lower bound of this integral should really be the radius of the ion. We should be integrating that interaction only starting at where we differentiate the ion from the surrounding environment. So let's call R, capital R sub ion, the radius of the ion. And then that's an integral we can do. We don't know the constant of proportionality, but it's going to go like Q squared over R ion. And indeed, remembering Coulomb's law as Q times Q over R, this indeed has units of energy. Q squared over R has units of energy when we are using these reduced units for the charge, which takes in those fundamental constants of 4 pi and epsilon naught. That has a very intuitive form. If you think about this process again, an initial ion polarizes a solvent, where that solvent has aligned itself with the electric field generated by the ion. So those vectors that I've just drawn could represent the field or the dipole that gets aligned with that field. If we take it to be the dipole, well, what do we mean by a dipole? A dipole is just charges separated over small distances. So by putting those arrows pointing towards the negatively charged ion, what we really mean is that the solvent has, in polarizing, brought up some amount of positive charge right next to that ion. Then it's no surprise that the interaction energy goes like the initial charge of the ion times the amount of charge that the solvent effectively brings to the ion in polarizing. Well, that's going to be, at least that's going to be, it makes sense that that's going to be proportional to the initial charge of the ion. And the distance over which those sets of charges interact is set by the scale of the size of the ion. So the solvent in polarizing brings up or accumulates some positive charge at distance r sub ion to that anion, for example. Now, because those dipoles don't align exactly, they don't bring up a full amount of effective charge, the actual response isn't quite as strong. There's some factor that has to account for the fact that two dipoles don't like to align parallel to each other. So there's going to be some compromise made with bringing up some amount of positive charge to that anion, but not a full Q ion amount. And if you do a proper accounting of those interactions, which you could go read about in electrostatics textbooks, what you'd find is that there's a constant of proportionality, which is something necessarily less than 1, which makes this Q solvation an equality. That constant of proportionality defines a constant epsilon, which is known as the dielectric constant. It describes the full strength of the solvent response. Accounting both for the initial polarizability due to a single cell, that alpha, but in addition accounts for all of the interactions between dipoles. So that constant epsilon, the dielectric constant, if that medium, if the solvent is very willing to neglect its interactions and polarize completely in response to a charge, that epsilon would get very large, and that would accumulate a whole 2 ions worth of charge out to the radius of that ion. that would be a case where the solvent is very polarizable, very willing to respond. In cases where the solvent is not very polarizable, where the interactions between dipoles overtake their willingness to respond, that dielectric constant is going to be very small. It's worth noting some kind of scales for this constant. So it's unitless. Depends on what the medium or solvent is. We made a little bit of a table in a vacuum. There was nothing too polarized, so that dielectric constant is 1. That would give me no solvation energy because there's no solvent to respond to that initial field. For a non-polar solvent, something like hexane, some organic, that dielectric constant is something like order 2. I only accumulate about half of the charge onto the surface of the ion. For something like water, very polarizable, that dielectric constant is huge. It's 80. 1 minus 1 over 80 is very close to 1. Water polarizes significantly in response to fields generated due to ions. So in fact, one could even argue that neglecting those interactions between dipoles in the case of something as polar as water is not a bad approximation. For something like a metal, in which all fields are screened, that dielectric constant is infinity. There are no electric fields in perfect conductors like metals. Okay, so the last thing I'll say is just to give this equation a name. Make that a little bit bigger. So the solvation energy of an ion due to a polar solvent, that equation there, that goes like Q squared. So both anions and cations are equally well solvated in this picture. The amount that it is favorable goes inversely proportional to their size. So if the ion gets very big, the solvation energy goes down. And depends on the material that is doing the solvating only through this constant epsilon. This is an equation known as the Born solvation model. Born's a name you might have heard of before. He was one of the founding fathers of quantum mechanics. Before he was working on quantum mechanics, he was thinking about ionic solvation. Okay, so that's all I've got for you today. We'll continue this discussion of ionic solvation by generalizing this perspective a little bit more to think about not just one ion in solution, but multiple ions in solution. Okay, thanks for your time, and all of you stay safe.